For today's class, we'll be looking into calculus, which is still a part of, let's say, advanced algebra. Suppose we have a function, let's say y is a function of x. This function can be a linear function, it can be quadratic function, it can be cubic function, it can be a trig function, it can be exponential function, or a logarithmic function. And for every function, we can represent them in a graph using the Cartesian plane. So we have the y-axis, which is the vertical axis, and we have the x-axis, which is the horizontal axis. So this is y against x. So for different functions, they have different graphs. For example, for a linear function, we have a graph like this, either going like this, if it's a positive graph, or coming this way, if it's a negative graph. For quadratic function, we can either have something like this, or something like this. For cubic function, we can have something like this, or something like this, depending on some condition. For trig function, if it's sine function, we can have this. If it's cosine, we can have something like this. So for every function, we can represent them on a graph. So let's pick a very simple function. Suppose we have y to be equals to, let's say, square of x. Y is x squared. This is a quadratic function. If you have to sketch this, we have something like this for the positive side. So it means as the value of x is increasing, y is also increasing, but not linearly, because of this square here. We call something gradient. Gradient or slope, and we use the symbol m to represent it. What is gradient? It is the rate at which the dependent variable varies with the independent variable. The way y varies with x. So it is the change in y-axis to change in x-axis. Although this particular one is usually used whenever we have a linear function. For example, suppose we have a graph of a linear function this way, and this is y-axis, this is x-axis. If we want to get its gradient, we pick 2 points on this line, then we trace this first point here, that's y1, we trace it here, that's x1, this second point, x2, y2. So the gradient of this line is what? The change in y, that's y2 minus y1, x2 minus x1. But it is different for a curve. For a straight line, the gradient is constant at every point. At this point, the gradient here is same as the point. At every point, the gradient is the same. But for a curve, the gradient changes from point to point. So suppose at this particular point, let's say where x equals to a, this point where x equals to a, what is the gradient here? To get the gradient of a curve at a particular point, we will have to draw a tangent, which is a straight line that will touch the curve at that particular point. Let's draw it. So at this point, x equals to a, this is the point of contact of the tangent to the curve. Then on this point, we can now pick 2 points. Point on our point here, then we get the value of what? y1, y2, same here, x1, x2. Then after we can apply that the gradient equals to y2 minus y1 over what? x2 minus x1. But in doing this, it means before we can get the gradient of any curve, we have to first sketch the curve. After sketch the curve, we go to x-axis. At the particular point, we trace to the curve. We now draw a tangent. Then we pick 2 points on tangent to look for the gradient. That step is too long. In order to avoid, sketching the graph, putting the tangent there, looking for 2 points on the graph for the gradient, there is a shortcut we can use. Because there are some functions that if we want to sketch, to take our time. So we need to look for a method whereby we can look for the gradient of what? Any function without sketching the graph. And that is the concept of differential calculus. Calculus is of 2 kinds. We have what called differential calculus, where our major interest is looking for gradients of different functions. Gradients of different functions. For example, this is what? A polynomial function. Linear, quadratic, cubic, quartic, septic, octic. All those are what? Polynomial function. We can also have trig functions. Function of like sine x, cos x, tan x, sec square x, cot x, They are all trig function. We can have function of e raised to the power 2x, e raised to minus 4x, that's exponential function. We can also have what? Logarithmic function. So now let's generalize first. So we are going to start with differential calculus, and we are going to use first principle to determine the gradient of a function. Then we generalize for every other function. Let's go to differential calculus, first principle. But before I move on, let's talk about how important gradient is. For example, let's talk about linear function alone. This is y, this is x. If I have something like this, in this line, it means the gradient is 0. What is it telling us? This means no matter the value of x, y remains constant. That's the meaning of this. So, if you have a graph this way, and we are told that the gradient is 2, it means for every one step increment in x, y will increase twice. That's the meaning. So, look at this curve. 1, 2, 3, 4. They all have gradients. But the one the highest gradient is what? Is 1. Why? Because look at the change in what? Y. Or in this case, look at the change in y here. The change in y is reducing. So the more the change in y, because gradient is what? Change in y to change in x. So gradient and change in y are proportional. If there's a large change in y, then the gradient is high. So anytime you look for gradient of a function and the value is high, it's telling us about the connection between what? The two what? Quantities, the dependent variables and the independent variable. So a layman, let me use for example, when you eat food, what happens? Your stomach gets heavy. The more food you eat, the heavier your stomach gets. So in that case, your stomach getting heavy is a function of the food you are eating. So if the gradient of your tummy being full or being heavy to food is high, it means you can eat very well. But if the gradient is low, it means you are a slow eater. Can you see what gradient can tell us? So now let's move to differential calculus first principle. Now, differential calculus, which is also called differentiation. So we have y function of x, y depend on x. So since y depend on x, you can tell me this. If there is a little change in y, if there is a little addition to x, let me call it change in x, there will also be a little addition to y. Since y depends on x, if there is an addition to x, there will be an addition to y. And our main aim is actually to get the gradient, which is change in y to change in x. So what are we going to do here? We know that y itself is f of x. We can replace this y with f of x. So f of x plus change in y equals to f of x plus change in x. We can take this to the other side. So it means change in y becomes f of x plus change in x minus what? F of x. Our main aim is to look for change in y to change in x. So let's divide through by change in x. But we have a problem here. And what's the problem? Let you see it here. Suppose we pick an arbitrary point here. This point here. This is x, this x. And this is y here. If we add a change to x, maybe this x is 3 for example, if we add 2 to it, then it moves to a new point, let's say here. So if from where this is origin, if my where is x, we add a little change, then this place becomes what? X plus what? Change in x. Then this point also becomes y plus change in y. So what we did here is, this represents the change in x. This represents the change in y. Change in y, change in x. And this is the curve that connects them together. So if we take this as our gradient, we are going to get inaccurate value. Why? For a gradient, the 2 points must be on the same straight line. As you can see, this point and this point, they are not on the same straight line. So this is the main straight line. So this bends a bit. This will be our correct gradient if this bent line is straight. And for this bent line to be straight, the change in x must be extremely small. For example, when we move from here to here, the change was large. If you have to change from, let's say, this point to this point, if you have to join this together, This is almost like a straight line. The closer change in x is, the curve joining them will almost be a straight line. So to get a perfect straight line, our change in x must approach 0. And that will lead us to what we call limits of a function. So when we limit change in y, change in x, as the x tends to 0, then this now will become what? Our gradient, our correct gradient. So in that case, we are going to set this change in x to be 0. But to understand this, we have to use an example. So when we limit change x to be 0, this becomes our real what? Gradient. And that gradient now, we don't use this symbol again. It becomes what? dy dx. So this is our correct gradient. To understand this better, let's take an example. Suppose we have a function y equals to s squared. So if we add a little change to x, there will be a corresponding what? Change to y. From here, what is y? Y is s squared. So we can replace this y with what? S squared plus change in y equals to x plus change in x all squared. Let's take this one to the other side. So change in y becomes x plus change in x all squared minus s squared. Let's continue. From here, change in y becomes, let's expand. This square of sum. So that will be s squared plus 2x change in x plus change in x all squared minus s squared. This s squared here cancels this s squared. So from here, change in y becomes 2x change in x plus change in x all squared. Note our aim is to look for what? Change in y to change in x. So with the Bible said by what? Change in x, change in x, change in x. So what happens here? This cancels this. We have square, so this one take the square away. So from here, it implies that change in y to change in x becomes 2x plus change in x. This will not be the accurate value. For our value to be accurate, we have to limit the y dx, or change in y, change in x, as the x tends to 0. When the x tends to 0, what happens? This one will go to 0, so we'll be having 2x. So this change in x, we are going to what? Turn it to 0. So at the end of the day, this becomes our dy dx. So therefore, it means dy dx equals to what? 2x. Finish. So it means the gradient of this function, y, which is s squared, is 2x. This is what we call using what? First principle. So there's a concept that you need to master before going in depth into what? Differential calculus, in order to use first principle effectively. And that is the concept of limit. For different function, there are ways at which to set the limit. So limit of functions. So but we'll continue as we proceed, we'll just put it inside there. So when I talk to limit a function, it means you set change in x to 0. So this is one example. Let's take another example on first principle, and from there we generalize. Suppose we have this example, y equals 4x cubed. Now we want to get the gradient of this function, the gradient of the function using first principle. So what are we going to do? For a little change added to x, there will be a corresponding what? Change in y. So y becomes plus change in y when there is a what? A corresponding, when there is a change in what? In x. So anyway, you have x, put change in x, there corresponding change in y. What is y 4s cubed? So replace this y with 4s cubed. 4s cubed plus change in y equals to 4 into, let's expand. This is cube of sum. You have to know that. You must know square of sum and also cube of sum. So this gives us s cubed plus 3s squared change in x plus 3x change in x squared plus change in s all cubed. When we expand this is what we're going to get. Now from here, let us expand. Let's remove the bracket at the right hand side. So here we have what? 4s cubed plus 12s squared change in x plus 12x change in x, this will be squared, plus change in s cubed. From here, sorry, 4 will be here too. 4s cubed cancels 4s cubed. From here, it means change in y equals to 12x squared changing x plus 12x changing x all squared plus 4 changing s all cubed. Next is to divide through by changing x, because our aim is to look for change in x to change in what? Sorry, changing y to change in x. So divided by changing x, divided by changing x, divided by changing x. From here, this cancels this takes the square, this turns the cube towards square. So at the end of the day, we will have changing y to changing x to be equals to 12x squared plus 12x changing x plus 4 changing x all squared. What next? We have to limit. We limit. So limit as changing x tends to 0, our changing y to changing x becomes dy dx. And how do we get dy dx? By turning everywhere it's changing x to be 0. This one turns to 0, this turns to 0. So 0 times this, everything here becomes 0. So we left with only 12s squared. And that is the answer. For the first example, y equals to s squared, dy dx is 2x. For the second example, y equals to 4s cubed, dy dx becomes what? 12s squared. If you have to try, y equals to, let's say, 8s cubed, you get dy dx to be 24s squared. How? It's a pattern. What's the pattern? For example, here, the coefficient of x is 1. So 2 times 1, 2. Then from this to remove 1, that is 1. Here also, 3 times 4 is 12. From 3 remove 1, 2. So if you apply same thing here, 3 times 8, 24. 3 minus 1, 2. So we can generalize. For any polynomial function, every polynomial has a monomial. What's a monomial? A monomial is an entity that has a coefficient, we have the unknown, and it has a power. So this is what we call a monomial. So the general way of what representing a monomial. So polynomial can have what? More than one monomial. If it has 2 monomial, binomial. If it has 3, trinomial. If it has 4, polynomial. So if you have any polynomial of this function or of this form, if y equals to ax all raised to power n, it implies that dy dx equals to a times n an. Then from n move 1, n minus 1. So this is the first thing you have to what? Put at the back of your mind. So with this, you don't have to go through the stress of what? First principle, except for theoretical question where you'll be told to use first principle. If you are not told to use first principle, you use it directly. So with this, we can differentiate or look for the gradient of any polynomial functions. Let's take some examples. Now consider the following questions. Here we are told, if y equals this, find dy dt. This time around it means y is a function of time or function of t here at t equals minus 1. So we are going to apply the shortcut to first principle. Since y equals to 3t cubed plus 2t squared minus 7t plus 3, dy dt becomes, apply the principle, 3 times 3, 9. Right t. 3 minus 1, 2. We do same for the next one. 2 times 2, 4. 2 minus 1, 1. We go. Here we have 1 originally. 1 times minus 7. 1 minus 1. Then for this 3, t is not there at all. We assume we have 3 raised to power 0. Because n raised to power 0 is what? 1. 0 times 3, 0. 0 minus 1, minus 1, 3 raised to power. But don't disturb yourself. 0 times 3 remains 0. Anytime we have a constant, if you differentiate a constant, you get 0. And when you differentiate a number whose power is 1, like when you differentiate t, the t will just go away, it will disappear. So plus 0. So in this case, it means we just negate the 3. And for this minus 7t, we just move the t and leave minus 7. That's the answer. But we are to look for the value at t equals minus 1. So from here, it means the y dt becomes NOAC t here, put minus 1. Minus 1 squared plus 4 into minus 1 minus 7. So minus 1 squared is 1 times 9. 9. Then minus 4 minus 7. So the final answer becomes what? Minus 2. That is the answer. For the next question, we can say we are given y to be 6s cubed minus 5s squared plus 1 all divided by 3s squared. We are lucky that we have a single entity that we can split. I think what we have is 3s squared up and this one down. It's very difficult. But for this case, we can just split. So it is allowed in maths to split the denominator in this form. 3s squared, 3s squared, 3s squared. So we are writing, so y becomes 6 over 3, 2. S cubed over s squared, we have x. Then we have minus 5 over 3. S squared cancels. Then plus 1 over 3. If I have 1 over s squared, indices, it becomes what? X to the power of minus 2. So this 1 over 3, then this 1 over s squared becomes x to the power of minus 2. So it must be in this case. What must be between them should be addition to subtraction. There must not be division. So if you have division, try to split it if it's possible. If it's not possible, then we cannot use direct what? Formula. We have to go and use other principle. But in this case, we can continue. We can look for the, we can differentiate straight. The y dx becomes, for this, I told you, if you have just ordinary x, neglect it. So that will be 2. Because here we have 1. 1 times 2 is 2. 1 minus 1 is 0. X over 0 is 1. So x is just disappear. This is a constant. Anytime you differentiate the constant, what happens? It disappears. So this one will go away, just like this 3 here. Then, the power here is minus 2. Minus 2 multiply 1 over 3. So minus 2 times 1 over 3 gives what? Minus 2 over 3. So minus 2 with 1 over 3 gives what? Minus 2 over 3x. Then the power here is what? Minus 2. Then from the power, remove 1. Minus 2 minus 1 is minus 3. So that's what? X power of minus 3. We either leave the answer in this form, or we try to leave it in form of the way the question was. We can continue by saying we are done, but we can simplify further. Because here 2 is common. I have 1 minus 1 over 3s cubed. How? This is it. We factorize 2 here, we left is 1 over 3, minus 1 over 3. X is 1 minus 3. X to the power of minus 3, same thing as what? 1 over s cubed. Minus 1 and 1 becomes minus 1. Then we have 3s cubed. That's how we come about this. We can still simplify this further, but I think we can leave it this way as our final answer. The third one is similar to the second. For the next question, we can still split. This becomes x to the power of 7 over x to the power of 4 minus x to the power of 5 over what? I said it's allowed. From here, y becomes what? S cubed minus what? X. Indices. 7 minus 4, 3. 5 minus 4, 1. We cannot differentiate. From here, the y dx becomes. We have 1 here. 3 times 1. From this 3, remove 1. There's 1 here. There's also 1 here. 1 times 1. Then we have 1 here. That will be what? 1 minus 1. 0. What's x equals 0? 1. 1 times 1, 1. So, meaning if you differentiate x, you get 1. If y is a constant, let's say 3, the y dx is 0. If y equals to x, the y dx equals 1. If y equals to x, the y dx equals 2. Now let's move on to other polynomial functions. Okay, next, suppose we have u, which is a function of x, and v, function of x also. Then we have y, which is also a function of x, such that y equals to u divided by v. What is dy dx? This is what we call the quotient rule. The quotient rule. Division of two functions. Now, y equals to u plus v. And our aim is to get dy dx. How do we go about this? We can use first principle, because that's the base of all gradients of function. For example, if we have y to be equal to, let's say, x divided by x squared plus 1. Unlike the previous examples, we can't split this. We cannot say this same thing as what? X over x squared plus x over 1. It doesn't work. Because of this plus. It doesn't work. We cannot split. So how are we going to look for the gradient of this function? We have to apply quotient rule. Let's prove it. Okay, let's go on first principle. So there will be a corresponding change in y if there is a change in u and also a change in v. What is y? U over v. So we can say u over v plus change in y equals to u plus change in u over okay, this is v actually. V plus change in v. Next is to take it to the other side. So from here we have change in y equals to u plus change in u over v plus change in v minus u over v. Let's write this as a single fraction. From here it means change in y becomes, the LCM here is v into v plus change in v. When this cancels this, we have v left, multiplying the numerator here, u plus change in u. Then this minus, v cancels this v, we have this left. That will be u into v plus change in v. We can continue by expanding. This will give us uv plus v change in u minus uv minus v change in. Okay, this will be u change in v. Everything divided by v plus v change in v. So this will obviously cancel this. So from here it means change in y becomes v change in u minus u change in v divided by v into what? V plus change in v. What next? We want to get change in y over change in x. So we'll divide by change in y over by change in x rather. So we'll divide this one by change in x. We'll divide the numerator here. Also, everything here by change in x. So meaning we divide this by change in x. That is also by change in x. We only divide the numerator, not the denominator. In math, if we have a equals to b over c, if I divide a by x, I will only divide b by x, not c also. But if I divide c by x, the x cancels. So meaning I'm only dividing a. So we're only dividing the numerator. So what next is to take limit. If you take the limit of this as change in v and change in u tends to 0, because the change we are adding initially, are the u and v. So anyway, you see change in v, change in u, they tend to 0. So this one becomes dy dx. So therefore, dy dx equals to, we have v. Now note, what we have here is actually a function, change in u over change in x. So this one itself, if you limit it also as change in x comes to 0, this one tends to what? Let me add that on to change in x also. Change in x, change in v, change in u tends to 0. So the whole of this turns to what? Du dx minus u. The whole of this turns to what? Dv dx over, then this one is standing alone, then this one will tend to 0. So I'll be having v and v left, v times v, v squared. So this is the what? Formula for quotient rule. Back to that example. Y equals to x over s squared plus 1. So what we have up is u. What we have down is v. So from here it means u equals x and v equals to s squared plus 1. In each case, we have to look for what? Du dx and dv dx. If u is x, then it means du dx is 1. Recall, if we differentiate x, we get 1. Also, dv dx we give us what? 2x. This one comes to 0. So after getting your du dx, dv dx, we cannot come back there. That's our dy dx. So from here, what is v? We have to slot in the value. V is s squared plus 1. So here we are having s squared plus 1. What's du dx? Du dx is 1. So we are multiplying s squared plus 1 with 1. V is s squared plus 1. Du dx is 1. 1 multiply x plus 1 is x plus 1. Then we have minus u. What is u? U is x. Into brackets dv dx. dv dx is 2x. 2x over v squared. V squared. What is v? S squared plus 1 all squared. So from here, dy dx becomes minus x times 2x is minus 2s squared. S squared minus 2s squared equals minus s squared. So minus s squared plus 1 over s squared plus 1 all squared. This is the gradient of this function. So whenever you have division of two functions, we apply quotient rule. So this quotient rule, when you have what? U over v. We can also have u times v, what we call product rule. So this quotient rule. Now let's talk about product rule.